Okay,
Perfect.
thank you very much. Go ahead.
Thank you. Sorry for the technical problem. So, okay, this is now sort of a continuation of lecture 1 without going to lecture 2, which is tomorrow, because Bernard and I were both a little bit behind our original schedule. But it's good that we have this time now. So we talked a lot about primordial black holes. Bernard told you a great deal about the history of these objects and how they were discovered and about some interesting and sometimes humorous aspects. And I told you yesterday about formation, and we had different formation scenarios. Let me just tell you, regardless of which formation scenario you choose, let me just remove this one. You choose, so much easier. Then you always need a large energy density, which then collapses to a black hole. That's common for all of these. Yeah. So be it from inflationary perturbations, probably with the help of this reduction of pressure, say using QCD phase transition. I will talk later on more about this, where when you have radiation domination at early times, and you reduce the pressure usually works against gravity. These overdensities have it easier to form a black hole, right? So primordial black holes are black holes, like we know from our classical GR course, but born in the early universe. And well, they can be formed by cosmic strings. I will tell a bit about this one. From bubble collision, I mentioned this. I have another slide on this too. But in all of these circumstances, but even in some particle physics motivated scenarios, what you do have is you have some mechanism that brings enough energy in a certain region of space. Okay, and yesterday we spoke about what the threshold is for the overdensity. So in a perfect fluid, I mentioned that basically, so if you have equation of sigma P equal alpha rho, and in this scenario, if you have sort of this was a Topper type constant overdensity, but it works for general overdensities, that basically the equation of state parameter controls the threshold in overdensity, which you need to overcome in order to have a collapse to a black hole. And sort of the most simple scenario is when you have a Gaussian spectrum, and that's how it looks. So basically the high-end tail of this distribution in which you have collapse to primordial black holes, right? Then we talked about a very old diagram, but it's of a similar type. Then we have multiple these days, and I will show you very recent ones where actually constrain this fraction beta. Yeah, let me just go back to this. This beta occurs a lot of times, which is basically how many patches or horizon patches of the universe underwent a collapse to a black hole. Right, at early times, there's this big overdensity within a horizon patch, and that collapsed to a black hole. In general, it's a region that collapsed. How many regions do we have? It's a fraction of regions that collapsed over the region that didn't do a collapse. Okay, and this is usually put in constraint diagrams. You have this beta versus mass, and you see there's different factors. I don't want to talk about all of them, but we have some additional constraints from Hawking evaporation that lead to some gamma rays where you constrain the abundance quite a bit. And then I told you that you can connect this constraint diagram and the constraints on beta, take the constraints on the amplitude of the fluctuations. And I also showed that, so the amplitude is here, and then again, it's a function of mass. And also I told you that, well, the large-scale structure constraints that we have are actually far, far out to the right, meaning at much, much larger scales. And also the amplitude of this fluctuation, which you know from the CMB, it was at this time of October, but we now put it quite fine, that is much, much lower. So, and then I mentioned that, well, actually, what we need is either sort of a blue spectrum, by which is meant one which increases as a scale decreases. So you go back in time and you bring it up to sort of to a large value in order to get enough primordial black holes, or you need some sort of feature in the power spectrum that, or in this spectrum fluctuation that has sort of a peak. So, yes. And this was another diagram we mentioned where we compared like the CMB scales, the scales that are accessible to this cosmic microwave background experiments or observations to the CMB, to the primordial black hole scales. And we see that they are sort of vastly different, and we need sort of a large amplitude of the fluctuations at much smaller scales or at much earlier times. So that's also the reason why it's let me just finish this and come back to this. It's also a reason why it's not in conflict per se to have the CMB as we see it and fluctuations at early time, because you could think, if I need these large fluctuations, massive density contrast of third or a half, which is probably closer to numerical simulation, which have been done recently, and the CMB fluctuation where you have 10 to minus 5, or this scale here is a few times 10 to minus 9, that you could say, well, you may be in conflict, but you would be in conflict if the scales were sort of overlapping, but you're at such earlier scales that you could have such a feature. There was a question.
Yeah, thanks. So I know you said you didn't want to get into all the constraints on the beta versus M parameter space plot. Could you give us some little hint about how beta is constrained in general?
Actually, we have another part of it. I will actually come back after the formation section to, there's a big part, I have many slides on constraints, but I can already tell you there are a few constraints that are sort of very strong. For instance, if you have black holes around solar mass or so, what they would do, they would also lens. They undergo gravitational lensing. So if you have a source and then the black hole passes in front of the source, and so between us and the source, they would sort of distort the light. And by not seeing these distortions, you could constrain the abundance. Also, by looking at gravitational waves, if you had really a lot of black holes, they would probably generate a lot of gravitational wave radiation. There are other constraints from, one is just to mention dynamical friction. So by dynamical friction, the black holes could actually sink in the center of neutron stars and eat up the neutron star. So when people looked at, at certain regions, say globular clusters, they look at neutron stars, and by us knowing about the existence of neutron stars, you can also put limits on the abundance. So it's just a few examples, but I will come back to this later and really in great detail. We talk a lot about constraints, but like lensing, mostly it's micro lensing, but not strong lensing. So micro lensing is when you basically have sort of an amplification of the light curve, which has an amplification for a short amount of time. So strong lensing would be sort of you have an Einstein ring or Einstein cross, but it's mostly micro lensing. There's also milli lensing, femto lensing, nano lensing. There's also lensings, but it's all based on the same effect of gravitational lensing. Okay. So then I told you that there is sort of a sequence of numerical works by which sort of this threshold density contrast has been derived throughout the time by numerical simulation, but later simulations seem to converge to a value of 0.45. So remember roughly a half of the density contrast, which you need for the spherical perturbations in radiation domination. To have to overcome this threshold, they need to be sufficiently massive, sufficiently overdense these regions, and then they would collapse to a black hole if they overcome this threshold. And another thing is, especially in this Gaussian picture, the Gaussian fluctuations, you see that the abundance of black holes depends exponentially on this value. So having, say, 0.7 and 0.45 makes a huge difference. You produce orders of magnitude more of these black holes if you have a lower threshold. That's why also I can already tell you why this the dip which you can have during the QCD phase transition of the equation of state parameter, which controls the threshold. So the threshold will go down, then the equation of state parameter goes down. Then you produce vastly more. And I will have a slide on the QCD phase transition data on a model that goes basically through all the cosmic history and looks at different phase transitions where you have these events. And then you could have interesting sort of enhancements in several places. So I told you about that an often made assumption, and the probably most naive assumption, which you could make, namely by just assuming sort of the mass of the black hole is roughly the mass contained in one patch, one horizon patch. This is actually not quite true. You have something it's called critical scaling. So in general relativity, when you have these collapses, they basically show a special dependence on the density contrast. And this is sort of has been found out by Schoptrick in the early 1990s. There has been a lot of later works. But I want you to draw attention to the fact that, well, actually, there's sort of almost there's no lower limit in this equation. So if the density contrast of delta is very close to the critical, so delta C means critical contrast, this black hole mass can almost go to zero. And there have been simulations that show that this relation, so here m over mh, so basically divide this equation by mh, then you have this and the left-hand side is here, the right-hand side is here, both in a logarithmic representation, double logarithmic plot. Here you have delta minus delta c, and you see that it's over 10 orders of magnitude, you see this scaling behavior. So this is really there, and actually what it leads to sort of an extended spectrum. In the horizon mass approximation, where everything is basically at the horizon mass, already in the sort of relatively artificial situation, when you just have one scale that collapses, you don't have really just one one set of black holes all at the same mass. You have a spectrum and the tail extends to quite low masses. So, and this, of course, has implications on how many black holes you have. Are causing some signatures that you may observe. Yes, there's a question.
On this last part, is that what on this last part, is this data or on the one with last slide?
So in this, sorry.
Or are you just plotting this function? I don't understand.
So again, this is what was this? This is this is not just plotting this function. This is recovering this function by doing numerical simulation. So I mentioned this yesterday. I was a bit quick because I talked about this yesterday, but I'm happy to mention this again. So this actually has been found out, I think, by a renormalization group analysis in the early 1990s, a message object. So, and then much later, so this paper is from 2008, I think, where there was numerical work a few years earlier even. Well, there's simple numerical work even earlier, but on this level of precision, where they really had, what they were doing, they were having, they studied a perfect fluid and a spherical overdensity, yeah, and they were tracing basically the collapse. They were setting up a whole nonlinear simulation on sort of how the collapse works in GR, and looking when we have a Schwarzschild horizon and when really a black hole forms. And by doing this, they actually found over sort of 10 orders of magnitude that this law, what has been derived on very different grounds, is reproduced. So this is something that is really there and really sort of numerically quite well understood. All right, so that's actually, but this is actually leading to the conclusion that it's basically impossible to obtain a monochromatic mass spectrum. Monochromatic means here sort of just a spectrum that has just one mass. So even if you come in with just say a scale that collapses, so just one single scale, which is not so realistic anyways, but if you do, you would have sort of a broadening, and this broadening can help you, but this broadening can also work against you and sort of run into very steep constraints, which are sort of active on a low end of the spectrum, but can also help you because it pushes this down and it spreads it out by going sort of under the carpet. So yeah, so, and let me just mention that there's actually a minimum mass which you can have for primordial black holes in the inflationary context. So look, primordial black holes which are produced before the end of inflation are basically inflated away. So that's the basic, what inflation does, it dilutes the abundance of these significant. They're basically exponentially pushed apart, and they don't play any significant role. And when you sort of look, what is sort of a minimum mass you would get from there, you could look, okay, when does inflation end? Yeah, and so that of course depends on the reheating temperature, and we know reheating temperature has to be smaller than roughly 10 to the 16 GeV. And then there's a formula for looking what is the minimum sort of horizon mass that we could get, and that is roughly a measure then for the minimum mass of the black hole. That's probably around 1 gram. Of course, there's this critical collapse, there's a spectrum, but roughly 1 gram would be sort of the lowest mass you could get with these black holes.
I'm sorry, why would the problem if they're diluted away and you make some big black hole that spread out and still have them?
Well, okay, it depends on if you're probably if you're super close to the end of inflation, probably then sort of this dilution doesn't it's not so strong, but generically it goes quite quickly to an abundance which is totally not notable.
Are you talking about the baryonic matter being diluted or the black hole being diluted?
Black holes. I mean, I think I mentioned this. I had this diagram before, right? I mean, so when you have these different phases of inflation, here's time on this side, right? And then you have the Hubble horizon, then you have then you have radiation domination here, and here's inflation, right? Right? And here's this reheating, right? And a typical scale is sort of pushed apart. In this diagram, it didn't do sort of exponential representation, but scales leave the horizon and they sort of really pushed exponentially apart, and sort of everything gets pushed apart in here. I mean, like this is way. I mean, we're talking about a phase which is way before radiation domination, and sort of, and of course, then here's matter domination. So here you have sort of a lot of here you have dominance of baryonic matter, but here's basically radiation domination. That is sort of happening way before, and then this is really pushed apart. I mean, it's diluted. Of course, I think if you're very close, you may probably get around of having far too few. But you're right. I mean, they're there, but for most for all practical purposes, they're basically sort of gone away. One can calculate. I mean, probably I think it's an exercise. To calculate the abundance of black holes produced at the end of inflation or close to the end of inflation, then you can see how much less you really have than you had before. And we can talk about it, and we can make this an exercise if you like. So, but basically, what's about inflation is when you sort of have a typical inflationary scenario where you have some potential, and actually, inflation generally produces fluctuations, and these fluctuations can be expressed in terms of the inflaton potential, and that can have different realizations and different effects depending on how the potential looks. So if you see that this goes like 1 over v primes, and I mentioned this, if you have an inflection point or a plateau, which something which is flat or where v prime goes to 0, yeah, then these fluctuations skyrocket. So this is really one way to produce in inflationary setups very, very large fluctuations. So there's inflation generally gives you density perturbations, and these perturbations depend on how the shape of the inflation potential exactly is. I will later on come back to specific shapes and what gives you large classical fluctuations and other large quantum fluctuations. But there, it's basically in inflation scenarios, it depends on how the potential actually looks. Now, I think we talked about this scale. Actually, I drew this, so I don't need to talk much about this again. So again, let me just repeat that the scales are sort of during inflation. Here we can have scale, there's time, and in this representation, the Hubble scale is constant. And when the Hubble scale is constant during inflation, here the Hubble scale sort of moves Comes up like this, and the physical scale crosses the as redshifted outside of the horizon, re-entering later, and when it re-enters and having a density contrast which exceeds the critical value, you produce a black hole. Yes.
So is the point here that things are out of causal contact during inflation and they come back to the causal
Yes,
contact?
absolutely. And yeah, if you have to, you can just think about the simplest thing is like 2 points, and if I put 2 points at a distance, during inflation, they're exponentially pushed away. And then after inflation, the universe doesn't expand as rapid anymore. So, and these points at some point come into causal contact again. And this is only then a collapse can happen. So it's only then causally allowed, because they wouldn't know about each other before these points. So when the gravity would be communicated between them. Now, yes, and so very early, so Bernard Carr, let me just open all of these things. So already in the early 1930s, he's not so old. Already in the early 1990s, so Bernard Carr was, I think, was his PhD student, Jim Litze, they were looking at some slower inflation and where perturbations are nearly scale invariant, and the perturbation spectrum has a simple power law form, so k to the n, some spectral index n, and if zeta and eta are very small, so this is almost 1. Now, I told you that you need these large fluctuations, so almost, there's the density contrast of almost, not order 1, but sort of on the way, so it's about a half. But we know from the CMB that we have fluctuations which are tiny, which are 10 to minus 5 on average. That means, so if you have this form, this k to the n, either n needs to be bigger, so that is when you go to smaller and smaller scales, you would reach at these small scales sort of a large amplitude. But actually what we observe in CMB experiments, like Planck has observed something completely opposite. And also you could then say, aha, I could make sort of a running. So if n is not exactly constant, I could probably have some running of the spectral index, which changes with k. So again, you bend it up, and I think you can probably generate large fluctuations at earlier times. But this also this gives a wrong sign. So actually, what we really need in most primordial black hole formation scenarios in the inflationary context is a potential with a feature. And I told you already that sort of an inflection point or a plateau would do the job, but you can have a more complicated setup. You could have, for instance, a hybrid inflationary scenario, or of course, I will later on talk also about cosmic strings, bubble collision, and all these things. And you could have something which is not of inflationary origin, but if it's in the inflationary context, you would have to have a certain feature at small scales in the inflationary potential. Yes, but I mentioned a few inflationary scenarios, but there are actually a lot of them. There's hybrid inflation, there's and this is like 2 fields, but then you can have really a multi-field inflation, there's running index inflation, there's a designer inflation, there's preheating, there's Axion Curvaton inflation, there's all sorts of, there's all sorts of things. There's actually, Bernard had a slide with, I don't know, it was filled, and small font was filled with sort of all of these sort of inflationary scenarios. It was by far not complete. I mean, there's so many, and you can't catch up with all these scenarios that have been proposed. But all have to have, if you produce primordial black holes via some inflationary scenario, all have in common that at some point you have some feature leading to large fluctuations. Okay, but are you lost? Because this is it's always a good question whether one is lost, but in particular when you have too many sort of inflationary scenarios, do I have always a certain, always a different mass function? Is there anything in common? But actually, yes, the latter is true. So it looks like that most of these mass functions that you get, here's df by dm, that's the primordial black hole dark matter fraction, and m is the mass. This is as a function of mass in units of solar mass. So And it turns out that most of these models, like the running mass inflation, for instance, the model, which are the colored lines, can be approximated by a so-called log normal mass function, which is as this shape. So it's a known function, and they are not exactly fitting, but most of these could be sort of approximated by a log normal mass function. You can use this to study constraints for extended mass function, because basically all constraints, most of the constraints which you see, if they have sort of the dark matter fraction on one axis and the mass on the other axis, they are basically only for monochromatic spectra. So this means for spectra that are are just having basically one mass of the primordial black holes. But like I told you, from the critical collapse and also from these different inflationary scenarios, you always have extended spectra. That means you have to have an integrated scenario, and then you make the scan over the width is sigma f and the peak mass, and then you can make this parameter plot. I will show you later some plots how that looks, but then you really have to do some integrated plots. But often most plots you see are really for monochromatic mass functions that are strictly not realized. Now this is actually similar to what I said before in a bit different terms. So here, if you have an inflaton, and say it's homogeneous, there's time dependent, and the time is here a number of equals, but fine for simplicity. And basically the field equation is like this. So you have the potential derivative of the potential is defined, and if the potential is flat, so if you have sort of piece of the inflationary potential which is sort of having this plateau feature here. Then before you have your slow roll phase where you have some small quantum fluctuations rolling down, and what happens when it reaches sort of this sort of flat part or inflection point? Then actually if it's really flat, then the derivative of the potential is zero by definition. Leaving you is so phi prime, phi double prime plus 3 phi prime equal to 0. And if you pay attention in kindergarten, you you see that this is an exponential solution which you get, and when you plug this in the expression for the power spectrum, you will see a lot of power, get really large fluctuations. Of course, this is not everything that is there. So once you have this situation, quantum fluctuations kick in. There's a really strong quantum fluctuations that have to be treated in a special way. I mean, there's some techniques that people use from so-called eternal inflation, some stochastic differential equations, rather complicated, to do sort of a complete analysis of this scenario. But this is just to show you classically it increases, but then there's also some sort of quantum effects that kick in that are really strong and need to be resummed to give a proper to contribute to the proper picture, and later on allow you to derive the final form of the perturbation spectrum. Yes, please.
Thanks. I don't think I'm quite understanding why PDHs get produced in this plateau region.
Well, okay. So, like I said, what do we need for having primordial black holes to be produced? Sort of, you have large fluctuations. The big fluctuation overcomes the pressure when you're in radiation nomination. What you need to have, you have some radiation pressure, and the pressure works against the gravitational collapse. And if you have small fluctuations, they would just be dissolved or just stay there. They would not collapse to a black hole. You need really massive fluctuations, like big overdensities that lead to that lead to a collapse, that overcome this environmental effect as the pressure, for instance. In this scenario, what I express these fluctuations amplitude is probably easier when I go back. So let's just go back. Slow. Yeah. So it's basically, yeah, so one can show, it's probably another exercise. So one can show that the overdensity which you produce depends on the potential. And the potential, if it's really flat, it produces really large fluctuation. That's something one can show. We can see first how inflation produces these fluctuations, and then you see how in certain parts of the potential the fluctuations have different amplitude, and in flat parts they usually have pretty large amplitudes. That's something you can just derive. It's something which is not too complicated to derive, but it's actually you generally produce fluctuation, but depending on where you are in the potential, where this ball rolls down, then you produce sometimes more, sometimes less. And for primordial black holes, you need large fluctuation. This you generally produce during sort of a plateau phase.
Okay, so just to make sure I understand what's going on, when the inclination potential is in this plateau, there are fluctuations that can produce, and then after inflation, those fluctuations come back into possible contact flaps and produce primordial black holes. No, or not quite.
Yeah, I mean, it's really when they re-enter again. So I mean, I have yes. So let's see. So basically, yes, basically when you have sort of these things leave here, and when you have sort of re-entering of the fluctuations here and there above the threshold, then they collapse to a black hole.
Yeah, that's great. Thanks.
Let's see. Okay. So like that. This. Yeah, but if you then, like I said, go through this detour and not only calculate the classical fluctuation, but really calculate the quantum fluctuation. There's a huge amount of this large amount of quantum fluctuation that you need to take into account. And when you do this properly, usually with some stochastic techniques, you'll find finally that sort of the amount of primordial black holes which you get is hugely enhanced. So here I put against beta, and here I put n, but you can also put scale. You see that one, where you just have sort of a classical calculation, which gives a certain form for one specific model. Doesn't matter which model it really is now, but you have sort of a plateau model. But when you sort of resum all the quantum fluctuations, you get a huge enhancement. You see, and this is like 10 to minus 50 or so. That goes to 10 to minus 20. So you see this in many orders of magnitude enhancement, which you get when you properly sort of do your resummation and put everything together. That's why I said quantum diffusion is sometimes called, or this large quantum fluctuation. This strongly enhances the primordial black hole formation. Now, actually, so this was all for inflation. But now you can also produce primordial black holes by many other scenarios. And one scenario is when you have phase transition, like first order phase transitions. What would happen in first order phase transitions? You nucleate bubbles. With these regions of which keep expanding and which are sort of where you go to the new sort of new vacuum, and then these regions can have a certain dynamics. So you have a certain rate of forming these bubbles of the new vacuum, and then actually it depends on precisely how much of these or how fast you form these bubbles. So if the bubble formation rate is too large, basically, so the entire universe undergoes this transition quickly and you don't produce primordial black holes. If you have a too low bubble formation rate, you would sort of have in a situation where these things very rarely collide. Remember, you need a large energy density in certain volumes, and this comes into play when you have the collision of these bubbles. And then you also got no primordial black holes. So if it's rightly tuned, so it's quite tuned scenario for most cases, you would get primordial black holes. And if you have this scenario, then the specific masses are sort of it's rather light. It's into the 3 gram at the dark report, when you have sort of phase transition there, first sort of phase transition of black hole, you would get 10 to 28 gram. At the QCD epoch has or leads to primordial black holes around the solar mass. Okay, so and this is actually for the first type of first order phase transition. Then your second order phase transition, the smooth ones or smoother ones, you this is a simulation which some people by Chris Burns. They, calculated basically the sound speed or the equation of state parameter here as a function of scale or time, and which you can translate in terms of horizon mass, because of each of these times, and then put time here, time, the mass of the horizon is different, and then you can express it in terms of the horizon mass. And during the phase transition, PCD phase transition, it corresponds roughly to a solar mass, a bit more, roughly a solar mass. I would have a dip in the equation of state parameter. It's now here W. Sometimes there's a bit different notation, but that would lead to a lowering of the to the threshold. And when you lower the threshold, many more fluctuations can come over, then produce sort of a spike in the abundance of these objects. So here's the primary black hole dark matter fraction on this axis, and here you have again the mass, and you see that we have sort of an enhancement. And also note that here above its point is a third, so you have just pure radiation domination, and during the phase transition you lower the threshold. Sorry, you lower the threshold, but you also lower the equation of state parameter, and that leads to a lowering of the primordial black hole threshold, and you have this sort of 10% dip, but you have 3 orders of magnitude more primordial black holes produced there. So you have a huge amplification, but just a small deviation from radiation. So this is something which is manifestation of this exponential dependence. And of course, if the phase transition is of first order, there's it's still a possibility. So if you sort of still in the allowed range of all the parameters we measured, you could have some lepton flavor asymmetry. And if you have this sufficiently large, it looks like the phase transition can still be first order. And if it's first order, again, back to this sort of bubble collision scenario. So let's see that. So, like I said, there's also these cosmic network before I come to cosmic strings. So before I talked about primordial black hole formation in the radiation dominated area. So you can have, for instance, in all of this part here where you have radiation domination, you can produce these objects, but also you can produce it in the phase of matter domination. And this can be also early matter domination. So for instance, imagine you have the Higgs, you have the inflaton, and inflaton decays in something heavy. If it decays in something heavy, this can linger around for a while and produce, before the radiation dominated area, even another matter dominated phase. And in this you have, like matter, you have no pressure. And when you have no pressure, of course, there's sort of nothing from this side to sort of prevent the colors, but there actually calculation is a bit different. So you have suppression by deviations from spherical symmetry. But nevertheless, it doesn't go exponentially down. Like I said before, it is when we have radiation domination, but you have a power law dependence. Still small, but it's much larger, and it's much sort of, it's not as much suppressed as it is in the radiation domination. And you can do precise calculation about the range. Let's not go too much into details. Again, with cosmic strings, if it's topic one-dimensional topological defects, they could sort of intersect with each other and produce closed loops. And again, if it in certain circumstances, it can happen that the whole configuration goes in its own Schwarzschild radius, and then it collapses black holes. Generally, the condition for forming black holes, if you bring a configuration within its own Schwarzschild radius, and then you have a black hole, and then you can calculate how the spectrum of, usually get a scale invariant spectrum, and the scale invariant spectrum has particular properties, how sort of the mass dependence of the dark matter fraction is. You can precisely calculate this, but this is basically the most mechanisms. Yes, please.
Would you mind giving us the cosmic strings for dummies version of that, please? I don't really know anything about string theory, so is there just a summary that's, I don't know.
Well, I mean,
it's probably extremely complicated.
Well, it's not per se what you know from strings theory. So it's not about these strings. It's like topological defects. It's a bit extending, so we can probably talk after this more in depth. But this is some, this is one-dimensional topological defects. It's just really one-dimensional objects that also gravitate and have some energy. And they could, after phase transition, be produced, and under certain circumstances also. So when they form these closed loops and come in their own Schwarzschild radius, produce these black holes. I mean, it's a bit complicated. I think Hawking wrote one of the first papers on this, and there's a lot to say, but I think, can we postpone this for the sort of after the,
Okay, that sounds great.
because there's a bit more I would like to finish, otherwise I need to ask for another lecture. So, but we don't want to do this. So, but keep in mind, these fluctuations, like I said, are extremely rare. And how rare is rare? So imagine it's like the maximum case you can have in primordial black holes if they are all the dark matter. You can't have more. If all the dark matter is made out of primordial black holes, that's the absolute maximum we can have. And say all of those would be at 10 to the 20 grams. Okay, so it's some mass. I could choose a different mass. But then, since let me just first admit, but so then in order to, I mean, then you can ask yourself, how many patches at early universe, in the early universe, do I need actually to undergo such a collapse? And this is actually only 1 in 10 to the 15 horizon patches that need to undergo a collapse. I mean, before that, you could ask, okay, well, what is if too many of these undergo collapse? That would probably look very different. I mean, then the universe would probably look very different because it's sort of a violent process, the collapse, but you don't need many. And one reason is that when you're in radiation domination, sort of the universe dilutes as the scale factor. So if you have radiation, so say, and density, so for radiation, density rho for radiation, that is basically scaling like the scale factor of the force power. It's a scale factor, I think, I'm sure. In the inflation and in the cosmology courses, you must have heard about the scale factor. So it dilutes as a scale factor to some power. But if you have, so primordial black holes are born in this phase, but they're actually matter. So so rho pdh scales like rho matter, so matter. Yeah. But this scales like the third power. So it dilutes like the volume, whereas radiation dilutes this 1 power to scale factor further. Now, and that's actually, so this is the case that you only need a tiny fraction of primordial black holes, of patches collapsing at early times, because you get the sort of the different dilution of them with respect to the environment they're forming in. So, thank you. Okay, so, and like I said, they are forming in a very extreme end of the distribution. Now, and they're deep inside the tail. So it's just a very small amount of them that undergo collapse. You're there, you have to, it's a distribution, again, a density fluctuation, you're sort of somewhere here. It's a cartoon, they're usually like very high sigma, they are usually very far into the tail. You will see when I just drew it in realistic numbers. So, but of course, when you always have this, and you are so far in the tail, you are very sensitive to non-Gaussianity. So if you start from a Gaussian distribution and sort of you only need a small amount of deviations in order to change primordial black hole abundance a lot. So, and what's more, I think shown by Chris Burns, that there's actually a strong coupling between long and short wavelength modes, in the sense that you could sort of have a back reaction of these sort of short wavelength modes, which you need for the primordial black holes, the small scales, I mean, small scales for primordial black holes, and you need and the modes that sort of produce fluctuations in the CMB. And basically, some models can be excluded by causing actually CMB perturbations of CMB fluctuation, which you don't observe. And so some models that have non-Gaussian pieces could actually have been excluded by this feedback effect, this nonlinear mode coupling. And actually recent papers which use this quantum diffusion, this reformation of all the quantum effects and also statistical analyses, there's a whole field which is, I think, often used in sort of insurance techniques, insurance fields, which is the array event statistics. So if you have something, if you count very, very rare events and look for the statistic of these, they're quite different. And then you're led to something which is very, very non-Gaussian. And this has just having an exponential case, so not like the Gaussian e to a minus and then the square of the density contrast, but you have some sort of just an exponential dependence. So it's very, very non-Gaussian. And so that leads to also a different in the production of these. So let me, before I think we should finish soon. Another source of deviations is when you deviate from spherical symmetry. So if you go to some sort of ellipsoidal model as a simplistic generalization of this, what generally would happen is probably similar to what happens in galactic formation case. You increase this delta is a critical threshold, and EC means ellipsoidal threshold, and C means just a spherical threshold. If you have something deviating from spherical symmetry, you generally increase the threshold. If you increase the threshold, you would produce less black holes. And of course, high peaks are likely to the high-end fluctuation are typically close to Gaussian, but in the meta-dominated case and also in other circumstances, you may face non-sphericities, and they could change the abundance also by different orders of magnitude. Here's the fraction of product universes, the function of mass, and you can see the green is the from some specific model, which has non-sphericities as opposed to the spherical case, to suppress it quite a bit. Now, let me just in the remaining few minutes and just start with the constraint. Yeah, probably, yeah. Let me just briefly say, yeah, I will stop very soon, very soon. Let me just briefly give a short overview about these constraints. I will continue tomorrow with this. So you have sort of constraints coming first of all by not overproducing, sort of not producing more primordial black holes than there is actually dark matter. That's the maximum you can have. There's constraints from lensing, constraints from gravitational waves. There's constraints from sort of if they evaporate from by Hawking radiation. There are constraints, and I will at the end of the second lecture we will talk about the interesting possibility of primordial black holes and particle dark matter and the whims they can say annihilate and around in halos around these primordial black holes, and that gives you a lot of gamma rays, for instance, which you if you don't observe them, you can constrain the abundance. Interesting also like seismic constraints, because if they are very small, they're very abundant and could hit Earth, and then you could shake sort of get an earthquake. Actually, there's papers on this. There's disruption, which I mentioned, and they think by dynamical friction in neutron stars, they could sort of eat up the neutron star. And there are CMB constraints and all sorts of things. And just briefly, then I promise to stop. promise to stop. So, and then you can go to dinner. So actually, this is how one constraint diagram looks. I was in paper of Bernard and myself in 2016, where you sort of have the dark matter fraction here, you have the mass, and then you have sort of a region which is constrained in terms of microlensing, in terms of accretion constraints, and this is the Newton star limit. But actually, sort of some of these limits are now thought to be wrong. So these femtolensing constraints went away, these Newton star limits went away, and also the WMF constraints went away. And this is now a very recent constraint diagram of showing the primordial black hole dark matter fraction versus mass in grams here, and there's solar mass. Solar mass is around here. So if you have gravitation wave limits, microlensing limits, but what's important here, you do have sort of different windows where you can put more or less primordial black holes in certain abundances, and a big open window to put basically all of the dark matter very easily is in this sort of asteroid mass range. That's where you can put nowadays what most people would agree, basically all of the dark matter. But I mean, you have some other windows they can put a bit, sometimes 20%, sometimes 10%, sometimes a few percent of the dark matter. So, and we will tomorrow talk about extended mass functions, and these are sort of then you know have different bumps sometimes, and then you can put can have total dark matter of 100% in primordial black holes, and yet have some sort of different ranges where you have these peaks. And so the very last point, and I'm really stopping. So is that these constraints are actually a projection. So in many areas, when you see this constraint diagram here, there's a ton of constraints. I mean, you can talk hours on this diagram alone. How the different constraints are derived from different, there's different characteristics these black holes show. But this is actually sort of a projection from physics active at different redshifts. So the sort of depending on what sequences you look at, like CMB distortions or so, they're probably at very high redshifts, and then you have like the lensings, which are very low redshifts. So bear in mind that these redshifts or these constraints are generated basically from physics active at different redshifts. So and that's I think I will talk about these words of caution later. That there's different uncertainties in these constraints, but I think let's do it tomorrow. And I think I already stretched my available time window quite a bit. I think I can do more. So but let me thank you for your attention, and then let's go for dinner.